couple of seats up here if anybody would like to come and grab these. One in the first row, one in the second row. There might be a couple more scattered through here. All right, so next up is the first of two of Dr. Martsberger's groups from the physics department.
Hey, I'm Drummond, and this is Hunter. Our project was Don't Go Break My Heart, and that was...
Yeah, so pretty much we analyzed the variation in 24-hour heart rate monitoring data. So we'll get more into that. Here's an outline for what we're going to be doing. We're going to go through what heart rate variability is, and then we're going to go through our experimental procedure, move into what is an ECG, and then a little bit about our analysis technique, which is called detrended fluctuation analysis, and what those results mean, which are called alpha values, and then we'll get to some of the results we got.
Okay, so what is an electrocardiogram? So electrocardiogram monitors the voltage across your heart. So when your heart beats, it actually creates an electrical signal that goes throughout the heart. As you can see here, it kind of propagates along. See where the wave hits, a bigger signal goes. And it's typically measured in millivolts and seconds. And it's used medically to determine like the condition of somebody. If they've got a good ECG signal, then their heart's performing properly. And here you can see the electrical propagation throughout. This is actually a rabbit heart, but that's how it goes. That's an action potential. And yeah, it creates that signal, and that's what our electrocardiogram measures, and that's what we want to look for in our heartbeats. So with an ECG signal, you want to see a Qrs complex, and what that is when your heart, the big bump right here is our main thing. So you've got a Q peak, R peak, and an S peak. And that's our main point of focus, but more specifically the RR interval. So that's the distance between this R peak and your next R peak when your heart beats. That's your Qrs complex. And what a heart rate variability is, it's the fluctuation in the time interval between heartbeats. So your heart's not going to beat consistently every time. So the distance between this heartbeat and this heartbeat was 0.859 seconds, and this one was a little bit shorter, and this one even shorter. So that's going to change, and we want to look at those changes over time and do more analysis on that. And studies have shown that a higher heart rate variability leads to a healthier heart, healthier person. And that's what this graph is showing. So these are the different values for your RR intervals. And this one, you can tell, is going up and down. It's varying a lot more than this one. And this data corresponds to this curve. And this data corresponds to this curve. And the top curve is a normal heart, and the bottom curve actually had congestive heart failure. So you can see that higher variability is better. And that's a study by C.K. Peng. And this is the data analysis process. So we obtained the 24-hour heart rate data, hand cleaned and obtained the EKG, the clean EKG signal, ECG signal. They mean the same thing. Then we obtained the RR interval data, and then we performed a trend fluctuation analysis. So we're going to start with obtaining the heart rate data. So we hooked up participants to a 24-hour heart monitoring device. That's this thing here. They strapped this to their body, and their electrodes would go from this, and that would feed information to your logger on the far right there. And then we could get that data onto a computer with the flash drive. They were educated on proper procedure on how to hook it up so that if it fell off ever while they were wearing it over a 24-hour period, they could put it back on. And they were told how to maintain a good ECG signal, which is what we want. And they also had access to 24-hour phone line in case something that they couldn't fix themselves went up, and we could get over there and reattach the electrodes or whatever happened. But yeah, other than that, all everyday activities were permitted during the 24 hours. So, so hand cleaning and obtaining the data. So why cleaning matters is because oftentimes you do run into problems with your ECG signal. And if our program can't read those RR values properly, then we can't do the analysis on it, and we get bad results. So you have to go through. I'll show you in a second how we clean. So this is an ideal. This is our actual data that we recorded, and this is an ideal ECG signal. You can see consistent Qrs complexes and easy. So the program would easily be able to read those R peak values. And what you want to look for is a poor signal and no signal. Those are the most common ones. And yeah, so how you clean is you go through, and this over 24 hours, this is only like 10 seconds of data. So you have to swipe through all the data and look for little discrepancies like this. And that's possibly where the logger, like I was talking to, the pacer they have on them sends the data to a logger. And if they drop the logger, you usually get a loss of capture of the ECG signal. So we have to find that, because if it doesn't read an RR value here, that creates too big of an RR interval, and that affects our analysis process. So you just highlight it and delete it, and so it goes from this to looking back to your ideal ECG signal structure. And this is just another example. Sometimes it gets a little bit choppy, but as long as we can see the R peaks clearly, we can analyze the data. And this just shows when you measure the RR intervals, you want to see a graph like this come out of it, and then we send that I send that graph to Hunter, and he does the trend of fluctuation analysis, and he'll talk to you about that.
So now we're going to get into a little bit about the analysis we're actually running here, which is the determinate fluctuation analysis. So the determinate fluctuation analysis, to make it really simple, just finds hidden behavior patterns in complex data where it wouldn't seem as obvious. That can be related here to this lion face right here being pulled out like that. It's kind of what DFA does in a pictorial sense. So DFA finds the lion. That's the key there. But the first step of performing a DFA analysis is that we obtain the RR data that Drummond has cleaned, and then we find the mean RR value, and we add up the fluctuation from that mean, and we obtain an integrated RR value. It looks kind of similar to the RR value, but this is just how far a given point gets away from the mean of the data. And our next step is we divide that integrated RR interval into a set number of boxes, or box number is kind of what we're going to call it from now on. And then we fit a line to the data in each of these boxes. And then we add up the fluctuation from each point to their corresponding line. And then we repeat this calculation for a certain range of boxes. It depends on if we're looking at our short term or our long term, which I'll get into in 1 second. And then we graph this as a log versus log of fluctuation versus log of box size. And then the slope of the fitted line to that data is the alpha value, which is what we get out of DFA. And that can be seen right here. So this is the whole process from getting the RR interval, or integrated RR interval, to dividing in boxes, all the way down to plotting and obtaining the slope of the line. And so I kind of mentioned the short-term and long-term alpha. Here, alpha 1 would represent a short-term alpha, and alpha 2 would represent a long-term alpha. And the reason we have this is because with pretty much all of this data, we always obtain two different looking lines. So to be consistent, we look at everyone's short-term versus everyone's long-term. So the slopes are consistent. And our short-term alphas were run from a box size of 4 to 11, and our long-terms were ran from 20 to 100. And here's kind of more about like what alpha does. So alpha uncovers these behaviors that I mentioned. And if we look at something like a random walker, which is this middle one, a random walker is a particle or anything that starts at a specific point and has a 50% chance of moving left or right from that point. And as we can tell, this walker's kind of just moving around randomly, it goes in either direction. Well, an anti-correlated walker the farther you get away from your original position, the more likely you are to return to your original position. And a correlated walker is the complete opposite of that. The farther you get away from your initial position, the more possibility you have of continuing to go further away from your initial position. The correlated walker can kind of be imagined like a ball on a mountain. If you push it off the mountain, it's going to keep going away. The anti-correlated walker can kind of be related to like a ball in a bowl. Like it's always going to want to come back down to the bowl, the bottom of the bowl. Well, these three characteristics can be seen within our data whenever we uncover it with DFA. For example, a random walker has an alpha value of 0.5, and it kind of like fluctuates a little bit from the mean, as you can tell, in comparison to the other ones. The anti-correlated walker doesn't fluctuate very far from this 0 point, and its DFA value, or its alpha value is pretty low at 0.3. And the correlated walker has a higher fluctuation from the x equals 0 line, and it has a higher alpha value of 0.7. So, long story short, the higher the alpha value, the more fluctuation you have from your mean data point. And here are so our results, we are still currently getting these alpha values. It's a very time-intensive process. The calculations take days, and as Drummond said, we have to hand clean the data, and that's going through 24 hours worth of data, probably 10 seconds, 20 seconds at a time. And it a few bad heartbeats, a few bad R intervals, and it throws the whole DFA calculation off. So we really have to be careful while we clean that. But we're getting really close to having all of our alpha values, and we can run our statistical analysis on that. And here's some of our preliminary data, though. So we have our participant number followed by their short and long-term alpha. As you can tell, all of them are kind of around 0.8 to 1, which means we have more fluctuation than a correlated walker. And this over here is actually the log of the fluctuation or the log of the box size for one of our long-term alphas. So in summary, we obtained 24-hour heart rate from participants, and then we cleaned this data and we performed a DFA analysis on it, and we have alpha values for almost all of our data at this point, or for almost all of our participants at this point. And we plan to use this data to group participants based off of surveyed information that we have of these people. We have a bunch of different surveyed characteristics that we plan on hopefully finding groups and trends in the data with. And do we have any questions?
When you chose the participants, did you pick participants that had any kind of tachycardia, or were they all people that had, was it random, or was it people that had normal heart rates, or did you find people that had, did anyone have particular conditions?
It was random, but we had them write down if they had any diagnosed conditions, so that when we were looking through the data and we saw discrepancies like that, we could see that, oh, it's because of their condition, and that we should leave that. That was more concerning for the cleaning process, because it looked irregular. We didn't really want it in our data, but if they had an actual heart condition, then that meant something physical, and if we ran that, we wanted to see that on our DFA process.
It was pretty much dual. It was noted, and then we would determine if it was if it would mess up our results at all, depending on the person.
Or if it would.
Or if we had to clean it differently or something.
Yeah. Make our results better even.
Yeah.
I'm curious, you were saying that you were testing if there were certain higher proportions of people based on different survey characteristics. What hypotheses do you have on those survey characteristics? What would be some of those survey characteristics, and how do you think that they would interact with the results? How did you imagine at the start of this that they would?
Yeah. So at the beginning, near the beginning, you kind of talked about higher heart rate variability. I mean, a higher alpha value corresponding to a better health. So we have survey information on depression and anxiety, as well as on memory, because this was connected to a study that was done last semester in Dr. Steinmetz' lab we have memory results on 2-hour memory test results on them too, and our hypothesis would be that the higher their alpha value, the better general health, the better memory, pretty much higher alpha, better person. Those are our hypotheses right now. Better health of superior human.
Yeah, no, but we want to connect. We want to connect healthy heart to a healthy brain.
Yeah, that's our
So that's the angle, and that's the survey information we took of.
Yeah.
But that's down the road.
Yeah, I need to recognize the left health out there. But
Do you look at all, is there a connection between average R values? So is there a connection between variability of the R values and the absolute value of the R values? With a person with a higher heart rate, say 100 beats per minute, versus somebody with a low heart rate, 50 beats per minute, do you expect there to be any difference in their variabilities?
We haven't really done any studies on that, really, but that'd be something we could look into for sure.
Most of the data, separated. A lot of people got up. It was 24 hours, so at some point it wasn't consistent. It wasn't short term, so a lot of people varied from really high heart rates to really low heart rates. So it'd be hard to look at. We'd have to do a smaller time frame to look at a healthy, lower beats versus higher beats. But as far as long term, we can't really separate that out because a lot of people either were exercising while they had the heart monitor, or taking medication, or doing other things.
Yeah.
So it'd be hard to look at that with this study.
We also do have 2-hour heart rate data from whenever they were taking the memory test, and so that might be a good place to look at that, because it was very stationary, very controlled result, sitting there the whole time. So if we're going to do that, that would be a place to do that.
Any other questions?
Yes.